Hello and welcome back. We continue our journey into neural networks and deep learning, and one of the very popular tasks is to do image analysis with neural networks, and this is what we use convolutional neural networks for. So image analysis with neural networks is about, for example, image classification. We can have, like, is it a cat or dog, or more seriously maybe, is it a damage and which damage type in our experimental sample. You can also do object detection, here illustrated with the lorries on the motorway. Where exactly do we find a lorry? Or we can have segmentation, where we mask sort of the instance of this car in this example. So these are all applications that we can do with neural networks. So how do we see? Neural networks sort of mimic a bit the way we as humans learn and see. And this goes back to understanding what we actually do. The brain, was found out in the 60s, has a sort of a receptive field. So it turns out that we don't really process images as a whole, but cells correspond to stimulus given to a stimulus in a given area, but not outside these. And also movement may yield stronger stimulus than static ones. So how does this relate to convolutional neural network? We also have artificial receptive fields in here. In feed-forward networks that we have discussed previously, each neuron was connected to all of the others. That means that we have far too many weights. Especially since the deep learning networks become very complex, we have too many weights to handle. What we also want to do is learn abstract concepts. Right? We want to build features. Remember, in deep learning the approach is that we don't use humans to engineer features, but we let this learn. So we need to make a way to learn abstract concepts like shape or edges. Like a dog is still a dog if you view it from a different angle or from a different part of the angle. So we need to identify what is like the dogginess of this thing. And one of the founding fathers of modern deep learning is Jan LeCun, and in 1998 he proposed the convolutional neural networks. And these are essentially a new network topologies of learnable stacked receptive fields in a way. Before we dive into how to build a convolutional neural network, we need to understand a bit more what a convolution actually is. Let's take a different example and go back to a measurement process. So generally we don't observe true values, but it's always combined, for example, with the resolution function of our instrument. So that means that we need to combine or convolve the true measurement with the resolution, and this is the convolution operator. So we have, for example, a Gaussian resolution to our measurement instrument, and then the value we measure is a combination of what's there in nature plus what we can do with our instrument. Now, how does this relate to image processing? Actually, we have the similar idea. We apply a function, our resolution function in our previous example, and we call it a kernel here, to each image element or to each image pixel. So we convolve, this is the convolution operator, the kernel with the image. And because it's discrete, we have two sums running in x and y direction. So here we have the kernel depending on the pixel in I and j direction and the image itself. And now we sort of apply this kernel to the image to get to a new value. So before we move to neural networks, we can understand the idea a bit better. For example, we could take a two-dimensional Gaussian function, illustrated here on the middle one, and apply it to an image. So what happens if we move this Gaussian function? So each pixel now gets a contribution from the pixel around it. The center one is still the strongest contribution, but it sort of gets washed out with the contribution from the other ones. And this is essentially Gaussian blurring. So we have this nice little cute dog and apply this 2D Gauss filter to each pixel, and we have a blurred dog. So this kernel is like a blurring filter, if you like. We can also do a similar thing to detect edges, and this is what the Sobel operator does. There we have two kernels to detect changes horizontally and vertically, And if we convolve the image of this bike, for example, with a Sobel operator, we can get the edges and identify where there are sharp changes that are related to where the bike ends, for example. So here we apply known filters or the kernel to transform the image. So far we have assumed that we just move in one direction and take one step at a time, and this is called the step size or stride. And we also need to be aware of the padding, because our kernel is larger than a single pixel. So if we apply this filter, the resulting image is smaller than the original. So one way to avoid this is to do padding. We extend the image with a 0 around the border so that the image has the same size and the kernel sort of goes outside a bit of the region of the original image. Now we can move to convolutional neural network. So the key idea is here that we have these filters, and this is where the convolution part comes in, and they are connected with image properties. So for example, we have seen that the Gaussian filter is associated with blurring and the Sobel filter is associated with edge detection, right? So in image processing, if you do it in Photoshop, you go one way. You have the image, you choose a filter, and you apply the filter to the image and observe the effect. The key idea of convolutional neural networks is to sort of reverse the process. You make these filters learnable, and you stack many of these filters. These are the convolutional neural network layers. You stack these filters in many layers. So when you put in an image, or rather a large number of images into these neural networks, what you want to achieve is that the network learns the relevant image properties. So for example, if you have a blurry image, it would learn that this is associated with a Gaussian part, or each image will have some sort of edges, so it will learn some sort of Sobel one. And if you have a number of these layers, the idea is that you learn small objects like lines and edges and corners, and then as you have a lot of these convolutional neural network layers, you learn more complex relationships. So how do we define these learnable filters? That is essentially done by having a very special weight structure instead of fully connected neural networks. And this is called weight sharing. And because essentially what we do is make specific neurons relate to each other by these weights, we can train it with backpropagation as before, so we don't need to invent a new training method as such. The key difference to traditional machine learning is then that we don't have handcrafted features or feature engineering, but we use part of the network to learn these features. Before we dive into 2D convolutions, let's have a very simple example and do it in one direction. We only have 2 weights per layer, and this is what we call by weight sharing. So we have the weight matrix, but everything is 0 apart from those 2 weights. So we have in our image, in our sequence, we only use 1D for now. We have these feature variables x1 to xn. But now we only have 2 weights, so we connect them pairwise, x1 and x2, x2 and x3, x3 and x4, and so on. So this is our kernel. And then we have several of these layers on top. Right, so we have the green ones to start with, and then the pink ones, and the next layer, and so on. But each layer only has 2 different weights, weight 1 and weight 0. So this is the main difference between going from a fully connected network to a simple 1D convolution. Of course, in images, it's more complex because now we have a grid, but it's the same sort of principle. We input the image, like the raw input, what we observe in our instrument, for example, in our electron microscope or from our camera, and then we use these specific convolutional neural network layers, and they do automatic feature engineering. They learn, for example, the edges and higher level features. At the end, we need to have a small, fully connected network. This is called the classification head, for example, because we want to discriminate between damage and not damage, or cat and dog. And this is why we need a small, shallow network in the end. So a deep learning network based on convolutional neural networks is essentially that we have a feature engineering part on the convolutional layers and a small classification head that is a fully connected network. To do this efficiently and we get it to a higher level of abstraction, we need the pooling function, right? We need to sort of retain only the most summary, the most relevant summary of the feature, and this is called max pooling. This has proven to be very effective, and we also need to, for example, learn that displacement and rotations and cropping, they don't contribute as new features. For example, imagine a dog that is slightly moved left or right, it's still the same dog, or it's slightly rotated, it's still the same dog. And this pooling layers allow us to build more abstract features over time, so we put them in between the convolutional neural network layers. So the simplest structure that Jan LeCun developed in 1998 was called LeNet, and you can see here in this illustration that it has a few of these convolutional layers illustrated, and on the right hand we have the softmax where we have 10 class that was used to discriminate the endless data set between handwritten digits of 0 and 9. More modern approaches, well, you can see that they become more complex. So the AlexNet that won a competition in 2012 has a lot more of these layers stacked on top of each other. Another more recent one is called ResNet, and here we have the introduction of so-called skip connections, so we have direct bypasses, and you can already see that we have different types of blocks of convolutional neural networks, and this is sort of the game that has been developing over the past decades or so to come up with architectures and connections and ways to combine convolutional neural network layers such that it becomes more and more performant. And as you can see from the illustration, that also implies that these networks become much more complex and also much larger. And as a large example, this is ConvNext that was released in 2020. They combine many design elements from ResNet, for example, and other network approaches. And again, here the idea is that we combine different elements of convolutional neural network layers in a better way than before, and this can lead to a large performance improvement. Notice that this was, for example, done in industrial research by Facebook and Meta and not in academic research.